Hi everyone, I hope you're all well and in good spirit. Now, in this lecture, what we will do is we will begin by explaining some of the jargon and terminologies used in 5G communications. So, as we move through the different generations of cellular communication, the terminologies changed. Some went out of fashion and other showed up, and it becomes confusing when we're not familiar with the jargon. So I wanted to kind of put that all together in one slide, and then you'll find it here. I think this could be useful for you. After that, we will then begin with the basic fundamentals of mobile communication, and we will begin by discussing the coverage of a cell, the outage. When will you have an outage in a cellular communication? The signal strength, how to quantify the signal strength, or what are the different categorization for the signal strength, how to assess it, its relationship to path loss and throughput. So we'll discuss that. And at the end, we will then move into beyond one cell and look at multiple cells. And when we do that, how do we model a network of mobile cells? So we'll talk about that, the different means for modeling a network cell, which one makes more sense, which one is easier for analysis, which one is more realistic, and so on and so forth. So we'll discuss that here. So on to the lecture. Okay, so in this slide, what we want to do is essentially give you some of the essentials, and particularly some of the terminologies used in mobile communications. And we want to do this because we are gradually unwinding with 4G and beginning the deployment of 5G. This will be gradual, and 5G will be matured in the years to come. And I would say by 2024, 2025, the network will be more mature. So it's very important to understand the jargon as we move to 5G, and also to appreciate the history and the different varieties of how the jargon of mobile communications varied from what we initially had with 1G and all the way to what we will have soon with 5G. So when we talk of mobile communication, you have some essential equipments and units that are needed to operate your mobile communication. You will always have some form of a tower. So this is a base station tower. It is a cellular tower. And you will also, of course, have your phone, right? Your smartphone, your other type of devices. And you want to have a connectivity between your tower and your phone. That basically forms the most basic explanation of what mobile communications is. And the connectivity that you have between both of them, between this device, which is your tower, and this device, which is your user equipment, when you get the signal, when you get the radio frequency signal submitted to you or transmitted to you from the tower, you are getting this. And this signal is basically referred to as the downlink signal, right? So you are getting a downlink. So anytime you hear the word downlink, it is essentially a signal transmitted from the tower to your device. Now, this signal could, in different places, typically what we have today are, they operate around 700 megahertz, 1.7 gigahertz, perhaps 1.9 gigahertz and 2.6 gigahertz. It varies from country to country, but these are some of the values that we have for us here in Canada. The signal could also go the other way around. It could go from the device itself, from the mobile device to the cell tower. And you are able to do this because you don't have a simplex communication. This is a duplex communication. And it's not a half duplex communication. It is a full duplex communication. A half duplex communication is a communication where you are only able to transmit at a certain time, and then when your time is up, the other person transmits, right? So it is, you split the time that you do your communication. This is a full duplex communication. Essentially what happens is when the signal is transmitted to you, it is transmitted with a certain carrier frequency. And when you send your signal back to the tower, you are sending it with a different frequency, and you do this in order to avoid colliding between the signals. Okay, so you'll be able to talk and listen at the same time, and the same thing happens by the tower. The other elements that you should understand, or you should learn of in mobile communication, is the different terminologies for the tower. So initially with 1G, the tower had the kind of most basic default terminology. It is referred to as BS, or base station. With 2G, the name changed to BTS, or base transceiver station. Again, it has the word transceiver, but you know, even in 1G it was a transceiver. Even in 1G this was a transceiver, but suddenly it showed up in the name, so it's referred to as BTS. And for 3G, the name changed to eNodeB. And so anytime you hear the word eNodeB, it means a cell tower operating with 3G. With 4G, it became known as eNodeB. And so this is a very important terminology to know. So you will hear the word eNodeB a lot, and basically what it means is essentially your cell tower operating with 4G LTE advanced, or LTE capability. And today with 5G, the terminology that will come about as we deploy these networks is gNodeB. Right? So gNodeB, G stands for 5th generation NodeB. So it kind of took this part here, and then it updated this one to G. Okay. So these are the key terminologies that you should know of. Now, I have to say to kind of mention what NR is. So NR is a radio access technology. Right, it's a radio access technology. This is essentially the technology for 1G. So when we say 1G, what was the standard or technology used? It was basically AMPS. There were others used in Scandinavia, but AMPS was the one that was also common. In 2G, it's essentially the technology or the standard used was GSM. In 3G, UMTS. There were others as well. In 4G, it's LTE advanced. And in 5G, the standard that is used is known as the new radio. So this is kind of the new radio access technology that we are using for 5G. The NR simply stands for new radio. So there's nothing creative about it. It's just, it's a new radio. It's a new frequencies that they are proposing for 5G. And that's why it's called NR. And this was developed by the 3GPP standardization body. The thing that you need to know is perhaps you're wondering, what are the new frequencies or the new radios that are proposed with 5G? So there are two new radios that are proposed with 5G. One radio is referred to as the sub 6 gigahertz radio, or sub 6 gigahertz frequencies. Another type of frequencies that you can have is the millimeter wave frequencies. Okay, and if you notice here, for the sub 6 gigahertz, you could be anywhere between 1 gigahertz to 6 gigahertz. But some of them are already used, right? In 4G, we already have a link operating at 1.7. We already have a 2.6. So the new ones that are introduced are 2.5 gigahertz and 3.5 gigahertz. These are the new frequencies that are opening up with 5G communication when we talk of sub 6 gigahertz. But we are also giving the capability of cell carriers to operate at millimeter wave communications. So millimeter wave communications, it means that you are operating at very, very high frequencies. Frequencies that could range somewhere between 24 gigahertz up to 100 gigahertz. This is enormous. It's very high frequency. But the one that will probably be deployed in different parts of the world is the 28 gigahertz. So certainly this will be deployed in Canada, 28 gigahertz and 3.5 gigahertz. These are the kind of the two new frequencies that are introduced here, but also around the world. Another jargon that I should mention is perhaps FR1 and FR2. It simply stands for frequency range 1 and frequency range 2. It's just another jargon that is added to your lexicon. So if you hear this, it basically simply means that we are talking of lower frequencies. And if you hear FR2, very, very high frequency. And we want to operate at both. So some applications will require lower frequencies, some applications will require higher frequencies. With higher frequency is what the key advantage, and we saw this and when we talked about path loss, is that the higher the frequency you have, the faster your communication will be. So you will get high throughput. So somewhere between 1 gigabits per second up to 10 gigabits per second in the 5G context. But nothing is free. So you get something, but you lose something. So the higher the frequency, the lossier your signal is, right? So your communication range will be smaller. You'll be confined to a shorter communication range. You cannot send a signal at a very long distance with 28 gigahertz, right? The communication range will be smaller because it is lossier. The path loss is will lose very quickly. And so the quality of your signal will diminish very quickly. So usually this is good for indoor applications. Some indoor applications, maybe also for some V2X applications in the city and so on. But in general, this is something that one should know. So it is good, but it has its limitation. And that's why you have both capabilities, sub 6 gigahertz and millimeter wave communication. Both of these topics, particularly this one, these are all hot topics right now in 5G communications. And there's going to be a lot of work related particularly to this, because as you increase the frequency, building the electronics of your device becomes very complicated. It's more expensive, it's more complicated, and there's a lot of technical challenges as you put your device together with very high frequency. Okay. Now, what happens in the channel, so essentially between your tower and your device, is referred to as the radio interface. So essentially what happens in the air, over the air. Okay. So for 1G and 2G, this simply was referred to as air interface. For 3G, the terminology suddenly changed to UU, uppercase U, lowercase u. So anytime you see this, it simply means that we're talking about the radio interface, so essentially the channel. And when we talk about 4G, the terminology became LTE-UU, right? LTE-UU for that. And in 5G communication, the terminology became NR-UU, okay? So new radio UU. Okay, so anytime you hear these different terminologies, you should simply know that we are talking of radio interface. Beyond this, what we want to discuss now is the device itself, the cell phone itself. So we have different terminologies for the cell phone itself as well, the units that are connected to the device. In 1G and 2G, the terminology that was used was MS. So anytime you hear the word MS, it basically stands for mobile station. For 3G, 4G, 5G, the terminology became the different units that are connected to the cell tower suddenly changed name to UE. User equipment. So anytime you hear the word UE or user equipment, it basically means some device, some radio or frequency device that can talk to a cell tower. And it doesn't necessarily have to be a mobile. It could be anything, such as a wireless router, a hotspot, or a mobile broadband adapter. So a wireless router essentially is like the router that you have at home, the router that you connect at home, but this router is not connected to a coaxial cable or is not connected to a fiber optics cable. It is simply connected with, it has a SIM card that is given to you by your provider, and then this router is connected to the base station. And then all the other devices that you have at home will get connectivity by connecting to this device. So if you have a printer that is wireless printer, you connect it to this device. If you have your laptop, you connect it to this device. Your wife's laptop, your girlfriend's laptop, connected to this device. Your children's laptop, they're connected to this device. Your TV, everything's connected to this. And then this one here will connect to the cell tower. So it's like your typical router, but the router is no longer connected through some cable indoor. It is connected through a SIM card like a cell phone. If you think about a wireless router, it's essentially like a cell phone with a tethering capability, kind of the same thing. You also have capability to perhaps use a mobile broadband adapter. So sometimes you want to get connectivity for your cell phone and there is no Wi-Fi, or you do not want to use a Wi-Fi. You could simply connect and get connectivity by connecting such a dongle. This is a 4G dongle. I suspect 5G will also have these kind of dongles where you could connect it to your device through the USB port, and you'll be able to communicate to get your internet and your connectivity with a cell tower, not with Wi-Fi. Right? So this is also another capability. Because now the options varied. It's no longer a cell phone anymore. The word mobile station is no longer used. The terminology user equipment became kind of more typical. Now, also I should perhaps mention the official definition of what UE is. So UE is any device used directly by an end user. An end user, somebody using it to communicate with the mobile cell, right? With a mobile cellular tower, any device. So that's kind of the official definition of what a UE is. So, you know, we are saying that UE is used for 3G, 4G, and 5G, but so as you see, even in 5G, the term UE is still used. But perhaps this will not be the case for a long, because in 5G you have different type of equipments that you'll be able to communicate with. For instance, you might have this headset that these goggles, these headsets that you put to for virtual reality or augmented reality, where this headset is connected to the cell tower. So if that's one application. You might also have applications where you have sensors, and these sensors are perhaps integrated in your body to tell your physician or your doctor of your blood pressure, your heart rate, and other aspects of your health to a doctor. And this is relayed from the sensors in your body straight to the cell tower. These are all then would be examples of end user equipment. This is a user and he's using the equipment. So the extension, the terminology end user equipment or UE would also kind of extend to this kind of applications, and perhaps also to cars, right? Because in the end of the day, connected in an autonomous car, it could perhaps be owned by somebody, so it could also be an example of an end user equipment. So I'm not sure if UE also applies to these things. Perhaps the definition will change with time, but in the time being, you could loosely also associate it with these type of application. By the way, I did mention eMBB, mMTC, and URLLC in previous lectures, and I hope you recall this lecture. In fact, it was in the last lecture that we discussed these things. So eMBB, it stands for Enhanced Mobile Broadband Connectivity. Essentially is all type of applications that allow you to have very fast data rates, so somewhere between 1 gigabits per second up to 10 gigabits per second. mMTC stands for Massive IoT, Massive Machine Type Communication. So these are the different type of IoT devices. Now, I did mention that some IoT devices can be referred to as UEs, but not all. So if you have, let's say, sensors in a parking lot, that's not a end user device, right? It's just a sensor in a parking lot. Although it does fall under mMTC or IoT devices, but it's not really UE. So that's kind of a thing that one has to be careful with terminologies. But essentially, it means all the different sensors that you have, whether in your body, whether on the equipment, whether it's your fridge, and other equipments that you have. And by the way, I should also mention that not all IoT devices will be connected to the cell tower. Some IoT devices might be connected using Wi-Fi. Right? Wi-Fi is another technology that allows you to connect your IoT device. Some might also connect using Bluetooth. So there's a variety there, but certainly with 5G, IoT will play a much bigger role in the sense that many of these nodes will be able to talk to a tower. So perhaps some technologies like narrowband IoT will allow you to connect up to 50,000 nodes to a unique cell tower. So that's enormous. So the difference between these two is that this consumes a lot of, or it gets a lot of data rate out of the system, very high communication, whereas this is very, very slow communication. So we're talking somewhere between kilobits per second. So very slow communication. But this has the advantage of lasting for a long time. So if you have a sensor and you put it with some battery capability, this battery could last somewhere between 7 to 10 years. So it will last for a long time before you will need to change the battery. And it also has very long communication rates, somewhere between 10 to 15 kilometers in some cases. As for URLLC, well, this stands for Ultra Reliable Low Latency Communication. And essentially this is when you require high reliability, so somewhere around 10 to the minus 5 and perhaps even higher than that. It could also range up to 10 to the minus 9 depending on the automation level. So if we're talking about level 2, level 3 automation, 10 to the minus 5 makes sense, but in more advanced automations you'll need a much higher performance. And you also it also refers to low latency, so somewhere around 1 millisecond to 5 milliseconds. So I just wanted you to be familiar with these terminologies. These are terminologies that you will keep hearing on more and more in 5G communications in the next 10 years. But also be mindful that the terminologies, they sometimes go out of fashion and sometimes new ones are introduced. So just be mindful of that. As you can see, the terminology changed as we went from 1 to 5 here. The terminology changed as we went from 1 to 5 here, and also here. Okay, and so don't be surprised if it changes even as we move into 5.5G and into 6G. Okay, let's move on to the next slide. As we continue on after seeing the terminologies of mobile communication, here what I wanted to discuss with you is what do we understand from the coverage of a cell? So that's kind of the most essential requirement here in order to do analysis and design of communication, is to understand what is the certain coverage region of a cell and how to model it. So in order to move along that, we need to understand this concept. So let's go and discuss this. So let's say you have a cell tower, right? So this is an example of a cell tower. Now, if you notice here, there's 3 different antennas that you have. So that's kind of the sectoring that you have with the cell. We'll talk more on that later on. But for the time being, just think of it as your cell tower. And this is the radiation that you have from your tower. If you look more in depth into the radiation, it looks like this. Right, so this is the radiation pattern that you have coming from the antenna. Now, perhaps it's a bit lower here. I should have put it a bit higher, but that essentially gives you a sense of how the radiation of an omnidirectional antenna is. So here, the antennas may lead you to believe it's a directional antennas in different direction, every antenna, but let's consider it to be an omnidirectional antenna. It radiates in all directions. In fact, it's not spherically. It doesn't radiate spherically, as we said with an isotropic antenna. Isotropic antenna, they do not exist in real life. This is just something that we use when we do analysis. Perhaps you recall when we did the gain of an antenna, we saw that we refer to the gain of an antenna as dBi. You have the sub next to the to B with an I, and it means that we measure it we measure the gain with reference to the isotropic antenna. And that's why we use dBi. In this case here, we're not looking at an isotropic antenna. We're looking at a real life antenna, an omnidirectional antenna, an antenna that radiates in all directions. And if you notice, the shape of it is like this. Now, this is the shape that you have. It kind of goes down from here and it goes out outward in this format. Now this has the shape of a donut. Geometrically speaking, it's a torus. That's the geometrical terminology that we use. But essentially, it's like a donut shape that you could have. Okay, and if we now look at this radiation and we perhaps cut it here. we cut it along here, and we see the cross section. We see the side view. We look at the vertical pattern. This is how the vertical pattern of this radiation looks like, right? So you have along the different angles, and then you see the how it looks like, right? These are different values of power. And if you look at it from the top, from a horizontal point of view, i.e., looking at it from the top here downward, this is how it looked like, right? So it's just it looks like a circle. It's not a perfect circle, but it looks like a circle, and that's the how the radiation looks like. Okay. Now, you might then say, well, what happens in real life? How does these type of radiation happen in real life? Well, in real life, we'll show you some examples, and then we'll see how to model it. So let's say we have some antenna, some eNodeB or gNodeB, depending on what the case might be. So this is 4G, this is 5G, and we are interested to look at the cell coverage from a top view, right? From the top, like this, in a two-dimensional way. I mean, this is not two-dimensional, but the footprint of the network, we will look at it in two-dimensional. So one example that you might have might look something like this. Now, you might say to yourself, well, hold on, why did I get this and not this, right? So you were expecting to get something like this, but you got this. Well, there are two reasons, right? The coverage of a cell depends on two key reasons. Number one, it depends on the power that is being transmitted by the antenna. So that kind of dictates the shape of your pattern. But it also depends on the different obstacles or the different things that you have around the channel. So if you have buildings, and you have trees, and you have other type of obstacles that inhibits or that hinders your signal, then you'll end up having things of the sort. Things like this, where you have certain holes here in stronger areas. So this could be perhaps caused by reflection, scattering, diffraction, or most importantly by shadowing. So these are the different reasons why you'll end up with a shape like this. So this radiation is shown because you are looking at the radiation of an antenna in a situation where the earth is flat and there's nothing else. There's no obstacles, there's nothing. This is how the radiation looks like. But if you put your antenna in a city, you put it in a certain environment, there's buildings, there's people, there's cars, there's different objects and different variable elements around you, then you'll end up with a coverage that looks more or less like this. This is one particular area. Now, let's say we deploy this cell in some other region, some other area. It might be something like this, because it depends on what you have in that specific area. So in this new area where we deploy this is how it looks like. If we deploy it in some other region, it might look more or less like this. And it depends on, again, it's very site specific, right? It depends on where you deploy your antenna. Okay, so it will never end up being something nice as such. But when we do analysis, what we generally do is we essentially average all these different type of possibilities for the coverage, and if you average it, you'll get something like this. Now, this is not a perfect circle, but it resembles like a perfect circle. So on average, we could say that the coverage resembles a circle. And this is why, in general, when we do modeling, we'll consider things like this. We'll consider the average shape of the coverage, okay? And this is what we will consider as we move along in the modeling. Now, one other thing that I would like to mention to you is the radius, right? The radius of your coverage. So let's say this is my coverage. It's not a perfect circle, but it looks more or less like a relatively okay circle. The radius of the average line here is referred to as the coverage radius for your connectivity. So if you go outside this radius, you don't have connectivity to this tower. You might be connected to another tower, that's a different story. But to this tower, you're no longer connected to this one here. Okay, so this is referred to as the coverage radius. And if you're interested, you could also see the coverage radius here and the coverage radius here. Now, mind you that these coverage radiuses are the same, but these two are not necessarily the same. right? This coverage radius is in a situation where you're only looking at the radiation from your antenna, and you're assuming that it's a flat area. There's no obstacles, there's no buildings, there's nothing. Whereas this is the coverage radius while taking into account the different obstacles that you have, and its average among them. So just kind of be mindful of it. Sometimes we just consider the same value, this coverage radius to be this in the analysis, and that's okay, right? Sometimes we just want to be to do something. Don't forget, as engineers, we're not scientists, so we don't look for always for perfect outcome. We want to estimate things as opposed to finding always the most perfect and the most accurate. We want to estimate, and therefore we sometimes cut corners, and that's okay. As engineers, that's okay. We could do that in order to find some answers, some solutions to what we're doing. Okay, so let's move on to the next slide and then discuss more what happens with the coverage and the different challenges that could happen during the coverage. In this slide, what we want to discuss is the concept of cellular coverage and cellular outage. How are they different from each other? What does it mean from a physical point of view? What actually happens when you are connected, and what actually happens when you are not connected to a cell tower? What are the characteristics behind it? What are the causes for not being connected? And this is what we will cover here. So in a real life scenario, as we discussed in the previous slide, you might have a coverage that will look more or less something like this. And we said there are two key reasons why this happens. One reason is that you have your radiation. This is delineated by the transmit power of your eNodeB. Right, so this decides how your radiation is, and therefore you have a certain shape for it, for the radiation of your transmitted antenna, your eNodeB. And the various curves and the various irregularities of the cell happens because of the different obstacles that you have in the channel. So we talked about it just in the previous slide. So this is one example, this is one instance, so you put this some area and this is what you get. So if you look here, if you have a mobile device and you are anywhere in this region that has this color, then you should have connectivity. Your cell is connected, you are connected to the cell tower, this tower, and you will be able to make phone calls, you will be able to also use it for data, right? So you might use it to access data, the internet access. Now, certainly, if you are closer to the base station, you will have a better coverage. You will have a better signal. If you are farther away from the base station, you'll have a worse signal. Don't forget that the quality of your signal is dependent on how far you are from the transmitting node. So in this case, in a downlink, this one here transmits, and you as a mobile device, you are receiving. And if you're let's say here, this point red that you see, the laser pointer, then your path loss will be smaller as opposed to here. If you're here on the edge of your cell, then your path loss will be larger. If your path loss is larger, you're still connected, but your quality of connectivity is weak. If you are here, you are connected and your quality of connectivity is strong. At this point here, your path loss is small and therefore you have a big receive power. In here, your path loss is large. You're losing a lot of dBs in the channel and therefore your receive power is small. And these are the things that you need to understand. Okay. Now, what happens is the following. If you look at this place here, this area here, as you can see from the delineated lines of the cell, well, it's not part of the cell, and therefore you are in outage. So if you have a mobile device here, as soon as you cross this line, you're no longer connected. So you will be totally in outage. You're no longer connected to the to this eNodeB. Let's look at another example. So this is another example. You have some base station and let's say a neighboring cell. So this is one cell, you have perhaps another cell here, and then you have another cell, right? So when you look at a city, let's say our city in Toronto, you have a lot of cells. As you drive or you walk or you take your bicycle or you ride on a bus, or you could literally see these different base stations. They're very obvious. You could right away identify a cellular base station. So here we are going along. We have one base station just next door. We have another base station, and this is the coverage of this base station. So this is another eNodeB or a gNodeB. And if you notice here, we have, if you're anywhere within this region, you have coverage. You are covered, you're connected, and that's fine. If you're closer, you have a better coverage. You're able to get a faster connectivity. When people talk to you on the phone, you could hear them properly. If you're farther away, you're very close to the border, your signal might be bad. You have to move a bit. Sometimes you have to tell people, can you repeat that again? I couldn't hear you properly. The signal is weaker. And that's when, but you're still covered. Now, if you look here, these areas, these areas here outside the cell, of course, you are not covered. You are outside the cell. You're not covered. And if you look, for instance, here in this area, it looks like a lake, but it's not a lake. It's still land. It's still things that you have here, houses, stores, whatever the case might be. You're still in a city, but you have no coverage. And the one key reason why this happens, these kind of holes that you will have in your coverage, is that you may have very large buildings that could completely shadow the signal to come in here. Now you might ask, well, hold on, why is it that I have a signal here but not here? Well, here maybe you got a signal because you got some reflection. You got some buildings here that reflected the wave and brought it here, but not here, right? So here you had buildings that kind of surrounded it, and for some reason, there's total outage in this area. So these things could happen in real life, okay? At the end of the day, you might ask yourself, how can I represent this analytically or mathematically? How can we explain when you are connected and when you are not connected, or when you're in outage? One very basic explanation is that you're connected or you have coverage when your received power, so let's say you have a mobile, your mobile will receive the power in dBm or in watts, or in dB, watt, whichever the case might be. But in general, when we talk of cellular communication, we will always pretty much talk of dBm like this. dBm, which means that this is a power that you're receiving. It is a power in watts, but we are converting it in dBms. Okay, we saw this. I hope you know how to get this. So the power that you receive, this is the power at your mobile. It is bigger than a certain threshold. TH stands for threshold. You can think of threshold as the sensitivity. Remember when we saw Wi-Fi and we saw how to detect a signal with Wi-Fi? We had to figure out if we are at the sensitivity, above the sensitivity of the receiver, or below the sensitivity of the receiver. So depending on the manufacturer of a Wi-Fi product, a device that has Wi-Fi capability, you could read its manual, you could figure out what the sensitivity is. And if you are anywhere above the value of the sensitivity, you are okay. So let's say you have a sensitivity of, I don't know, minus 70 dBm. It means that if your received signal is minus 69 dBm, you're connected. You're okay. You're connected. But as soon as you go minus 70.5 dBm, minus 72, minus 73, you are no longer connected because you are going beyond the sensitivity of your Wi-Fi device. The same thing applies with mobile communication. So if you are above a certain threshold, you are no longer connected. And if you are below the threshold, you are generally connected. Now you might say, well, what is the threshold in general in mobile communication? It varies. It really varies from a carrier provider to another. It varies also from different mobile devices from another. But in general, the threshold that you could consider is minus 10 dBm. Minus 10 dBm could be the least, the absolute minimum threshold. So if you are below minus 10 dBm, forget it. You're not getting a signal. You are in outage. If you're above minus 10 dBm, you're good. If you don't like minus 110, you like to memorize minus 100 dBm, that's a good way to memorize it as well. I think it's fair to say that if you have minus 100 dBm and above, you should have a reasonable signal, perhaps 1 or 2 bars, and that should be fine. Right. So, and if you go beyond that, below that, then you're not good. And then this one is essentially the power that you receive. The power that you receive, you could just identify its value. Now you are disconnected. You're disconnected when you go below the threshold. So when you go below 110 dBm, you're disconnected. So let's say you have minus 112 dBm. You're disconnected. You're in outage. Okay. So that's kind of a basic definition of how to know if you are connected or you are disconnected. And we saw this, right? We saw this perhaps not in the context of mobile communication, but we saw it in the context of Wi-Fi connectivity. Remember the problems that we solved when we did the link budget? These are the things that we worked on. In fact, part of these questions also showed up on your midterm exam as well. Okay, so let's see the possible reasons for outage. I mentioned it to you right now, but I will want to show it to you in a written way so you have it in a more clear fashion as well. So one key reason for why one could have outage is that the transmit power is limited. Right? So your tower here has a certain power, and it doesn't transmit beyond that. So it's a limited transmit power. In general, cell towers will transmit at around 40 watts, perhaps. That's kind of the typical thing, perhaps a bit more, a bit less, but that's the typical thing. Now, if you go less than 40 watts, well, your radiation will be smaller. Remember the tire that we saw earlier, or the torus or the donut-shaped radiation? That will be smaller. And if it is smaller, it means you have less coverage. So that could be one reason why you have outage. The cell size of your antenna is smaller. Right? Not all antennas have the same coverage. Maybe I mentioned it before in the previous lecture, or not all cells have the same coverage. You have some cells that are that will give you large coverages in the kilometers, maybe 1 kilometer, up to 1 kilometer. And then you have smaller cells that will give you less than perhaps 500 meters. So it depends on the type of coverage, and this is defined. This is specified by the transmit power of your eNodeB. Okay, so this is one aspect why you might be in outage. Another reason why you might be in outage is that your UE, your device, is not close to the eNodeB. Right, so this is another perspective of kind of saying the same thing, but your device is not close here. So let's say you have a device, but your device is far. Right? If you're far and there's no other base stations here, well, you won't be in any coverage. Here, there's no base station, so you're not covered. And then this one here, you're too far from it, and you're not covered. So the range is way far away from the base station. So that's one reason. Another reason for not having coverage or for being in outage. Another reason for being in outage is that there is a lot of issues on the channel. There's the fading, the impact of fading is strong. So one important reason when we look at outage is shadowing. Shadowing is caused by the different obstacles that you have. For instance, a building, especially if the building is made from metallic structure. It could be concrete as well, but metallic is even worse, right? So this will completely hinder your signal. Perhaps some of it will pass, but in general, it will hinder it. It will shadow the signal. Okay, it will shadow the signal, and you will have your performance will be bad. Other reasons that could happen where outage could occur is in deep fade. Deep fade is there are certain areas within the cell or within a communication where you are completely out, right? So you go in this area, it's like a black hole, right? I mean, this is kind of an exaggeration, but you go there, there's absolutely nothing. You cannot get a signal. The environment is so protected. There's a lot of structures. There's a lot of items that will hinder your signal. You will be in deep fade. So in these areas, you generally have a lot of buildings, a lot of infrastructure, a lot of moving objects, perhaps vehicles, pedestrians, trees, bushes, vegetation, all of them kind of coming in together in a very intense way, and then you'll be in deep fade. For areas where you have deep fade, well, you simply need to move away from that region to regain your signal. So in this area, this could be kind of an example of an area where you have deep fade, and then as soon as you step out of it, you're back into connectivity. Okay. Other reasons why there could be outages is again I mean, perhaps we talked about these different attributes of channel fading. You have shadowing, that's one aspect that will hinder your signal. You have reflection, where you get a signal, it touches the building and it gets reflected. So you're intending to send it to somewhere here, suddenly your signal goes somewhere else. Or you might have a scattering. And scattering generally happens when your signal hits small objects, right? So these small objects could be, for instance, bushes, small trees, or it could be infrastructure that you have on the streets, or like a traffic sign, like this one here. You see a traffic sign, it touches it, it's a small object, and then suddenly the signal travels in completely different areas. So this is all different ways that could vary the type of coverage that you have, and to the extent that it could also bring you into outage. You also have the phenomena of diffraction. So diffraction generally happens when your wave, or your electromagnetic wave, or your signal hits a sharp edge. So in this example, you see a mountain in a city. You don't have mountains, but you have buildings, and these buildings, they could have sharp edges around them. So if your signal hits a sharp edge, again, the signal will kind of get offset in a different direction. It wants to go here, but suddenly it touches a sharp edge, and then it bounces somewhere else, and it bounces somewhere else, right? So these are all reasons why the coverage will vary, will be very irregular, and then you will have potential areas of outage. Another reason for getting outage is perhaps radio frequency interference, or RFI. Now, interference, we talked about it before, and we said interference is caused by other devices that operate in nearby operating frequencies or bands, and that causes interference. Or it could be similar devices that overlaps with the channel. So there are multiple reasons for interference, but these are some of the reasons. And if you have interference, what happens is your SINR, your signal to interference plus noise ratio, will drop. Right? So don't forget, you have signal on top, the good stuff, and in the denominator you have all the bad stuff. So you have your noise and you have your interference. If you want to eliminate noise so that we focus only on interference, then you might only look at SIR, and you have your signal on top and you have interference in the bottom. If you have a lot of interference, it will be big, and if at the bottom, the denominator is big, then the SINR will be small. And if SINR is small, that's another reason for getting an outage. Right? So that's also important to know. Now, so perhaps this is also a segue to mention this to you, that using SINR metric provides a more accurate assessment of coverage or outage. If you see here we said that in order to know if we have coverage or outage, we only look at the power received, right? We only look at the signal that I got. What is its power? Am I above a certain threshold? Am I above 110 or 100 dBm? If I am above that, I should have connectivity. If I'm below that, I don't have connectivity. Right? So we kind of said this is it. And that's fine. This is what generally people do. But if you want a more accurate view of being connected or whether you're connected or whether you're in outage, is essentially, it would be better for you to look at SINR. SINR takes into account interference, whereas in here, we don't take into account interference. This essentially only looks at your path loss, and perhaps if at best it might also take into account shadowing, right? So that's how you get this one. Now, I have to admit that quantifying interference is not easy. So if you talk about real life, well, how on earth are you going to know all the interfering devices around you? You're not going to know that unless you're doing this in a controlled environment. And in general, this is not the case. You're in an area, real life, right? We're talking about real life deployment. You deploy your cell. You don't know the other interfering sources, right? You do not know the other interfering sources. You might be able to look at it on your spectrum analyzer, different signals that you're able to detect, but in general, you don't know these sources. So what you could end up doing is either estimating what the aggregate interference is, and then come up with some estimate for it, and then figure out the SINR and then identify if your SINR at the receiver is above a certain SINR threshold. So that's one way of doing it. Other way of doing it is simply to look at the receive power, to look at the threshold, and that's it. And then to perhaps take into account path loss and to take into account shadowing. And that's fine. Remember, we said earlier that as engineers, we want to get some result. And sometimes what we will do is we will try to get the result in a rough way. So it's not 100% accurate, although you want to be accurate as engineers, but sometimes being 100% accurate is impossible. So we might relax the condition of identifying coverage or outage by simply forgetting about SINR and simply looking at it from only a path loss and a shadowing point of view. Okay, so I hope that that's clear. Now, so maybe I should mention it again in case you guys forget. I mean, you do recall that we saw this in the link budget, that the power that you transmit is equal to the power received plus path loss, right? I mean, that's what it is. Plus path loss. And therefore, if you want to find the power received, what you do is you simply isolate for the power received. So you could do the power transmitted minus the path loss, right? Power transmitted minus the path loss, and that kind of gives you the value for your received value for your received power. So these are the things that we saw in link budget, and the same thing applies here. And again, if you want to take into account shadowing, that's also not bad. There's nothing wrong with that. In fact, it will give your result an accurate view of how to do it. So if we only look at shadowing and path loss, we are in fact looking at it from a large-scale perspective. We're not looking at the nitty-gritty, small-scale impact of reflection, scattering, and diffraction. We're only looking at this, and we're looking at the power received, and that's fine. That's fine to give you a general view of whether you have connectivity or outage. So I hope that kind of helps you to see how real life coverage or outage is. And now on the next slide, we'll discuss how you see coverage in outage in, let's say, a mobile phone. And then we'll explain that a bit. In this slide, I would like to show you the concept of coverage or outage, but now specifically with numbers, and specifically for mobile communications. So we'll show you this, and hopefully you'll get a better understanding of what coverage means now with specific numbers. So if you see this, you have your base station or your eNodeB or your gNodeB. And assuming it transmits in an omnidirectional way, so it radiates in all directions. Of course, I have to mention that now with 5G, we will have directional beams as well, right? So you will have a specific beam that is directional, but in this case, let's just assume that it is an omnidirectional antenna. So you have an omnidirectional antenna; it radiates everywhere. That's why you have these circles that go around it, concentric circles that are going all the way. And if you look, you have kind of a scale of the power received. So this is the power that you receive on your phone. If you're here, the power received is minus 50 dBm. If you're here, you are minus 60 dBm. If you're here, minus 70 dBm, and all the way to minus 110 dBm. So here the M is missing, but M should be here everywhere. So this is not in dB, this is actually in dBm. And as you can imagine, the more you go, the farther away you go from the base station, from the eNodeB, the less the quality of your signal. Right? Your signal becomes worse and worse. It becomes poor quality up to an extent where you have no signal. So let's even see it more precisely. So if your signal, the receive power is anywhere less than minus 60 dBm, it is, not minus 60. If it's above minus 60 dBm, no, sorry about that. If it's above minus 60 dBm, so let's say minus 50, minus 59, minus 58, whatever it might be, anywhere here, your signal is generally considered excellent, right? So you'll have your 5 bars on your phone. And if you are anywhere from minus 60 dBm to minus 75 dBm, your signal is considered good, but it's not excellent, right? So in general, your phone will show probably something like 4 bars. And if you have anything between minus 75 dBm to minus 90 dBm, the signal is considered fair. So your receive signal on your mobile is fair. You have 3 bars on your mobile. And if you have anywhere from minus 90 dBm to minus 100 dBm, now your signal is not good, right? It's actually poor. You're still connected. You still have connectivity, but you're at 2 bars, and the quality is gradually diminishing. And if you have anything below that, so between minus 100 dBm to minus 110 dBm, well, now your signal is very weak. And in fact, to visualize it to customers and to people looking at their phone, you'll probably see only 1 bar on your phone. Okay, and if you go below minus 110 dBm, it will be completely an outage. So you won't get any signal. Now, just so you know, because I remember one student mentioned this in class, that some of the cell phones, they have 4 bars. They don't have 5 bars, and some have 5 bars. So I don't have an iPhone, but other friends and colleagues and family members that have an iPhone told me that they see 4 bars. And that's okay. It's just the way that that it's manufactured. It's manufactured with 4 bars. So this is basically kind of scaled down to only 4 items. As you can see here, perhaps poor, no signal, poor, very poor, poor, good, and excellent. And when you don't see anything, well, that means it's gone. Whereas here we see more descriptive, because with Samsung phones you generally see 5 bars. So that's just the way the different manufacturers design their device. So that you shouldn't worry too much about it. But in general, this is kind of the description that we have in terms of power. So one thing to remember, as I said to you before, considering minus 110 dBm of receive power is basically the really absolute threshold after which your signal is completely in outage. Other things that we could kind of see here is the following, is that when you're in this region, when you're in the good, excellent region, you are generally, your mobile, because you're here, you're relatively close to the eNodeB. So you're very close to the eNodeB, and that's one thing that we can identify with a good signal, is that you're actually close to your cell tower. The other thing that is important to identify is that because you are close to the cell tower, by the way, you're close to the cell tower with whom you're communicating. You might be close to a cell tower, but perhaps that cell tower is not the one that you have the subscription with, right? The cell towers, they belong to whoever carriers operate their antennas on. So perhaps you see a cell tower, doesn't mean your mobile is connected to that one. You're connected to the closest one that your mobile provider has an antenna in it. So if you see a cell tower, not every cell tower will belong to your carrier. So just be mindful of that. So anyways, if you're in this region, you're close to the eNodeB, you have a small path loss, and also your signal is very strong, right? You can see this by the bars here. You can see it by a strong, a big receive power. Right? So here, this is a small receive power. This is a big receive power. because it's like degrees, right? It's like looking at degrees Celsius, right? If you have, I don't know, minus 25 degrees Celsius, that's very cold. And if you have minus 5 degrees Celsius, that's actually very hot. So it's kind of the same thing when you look at this. When you have minus 10 dBm, that means the value of your receive power is very small. Whereas when you see minus 50 dBm, that means you have a strong receive power. So this is kind of a review of how the dB scale works. So in this region, you are close to the eNodeB, you have a small path loss, and your signal is strong. Okay, your receive signal, the power that you have, your received power signal is strong. And in fact, you can see this from this equation, right? I mentioned it in the previous slide. The receive power, these values that you see here, the receive power, this is your on your mobile end, is equal to the transmit power, whatever this thing transmits, this thing. In this case, this one is transmitting, this guy is receiving, this is your mobile, this is your eNodeB, minus the path loss. Now, remember where we got this equation? This is basically from the first equation, where we saw earlier. The only thing that is missing here is the gain for the antennas, right? You don't see the gain for the transmit antenna, the gain for the eNodeB, and the gain for your mobile. And in fact, you don't see it because the gain for an eNodeB in general, if you're omnidirectional, you're propagating in all direction, your gain will probably be very close to 1, right, in linear format, or 0 dBi. So that's why it's gone. It's gone. And the gain of your mobile could also be very small, right? Perhaps somewhere between 0 to 2 dBi. So we could just consider it as 0. So that's gone. And therefore, when we write the equation, we could simply simplify it and simply write the receive power at the mobile is equal to the transmit power from the eNodeB minus the path loss. So this is kind of the dB representation of this. If you were to write it in linear format, you would simply write power received is equal to the power transmitted over the path loss. Now, like we said before, if you want to include shadowing, that's also good because you want to include some, you want to take into account at least the large scale component of fading. That's fine. You could simply add here. You could simply add plus epsilon. And that would take care of your shadowing, and your epsilon will have a log normal distribution. Okay, that's how it's modeled. And in fact, in the log normal distribution of the epsilon, what is key in order to identify your shadowing, it's really the variance of your shadowing. How do you get the variance? Well, that's the question. How on earth do we get the variance? There's ways and techniques to do that, and we'll show it later on in the lectures. Not in this lecture, but in future lectures. So perhaps the next video or the one after that. I'll explain you how to find the value for the shadowing, the variance or the standard deviation of shadowing, and that becomes very critical. Okay, so you have a strong signal, and you can see this because of this. Your path loss is small. This is small. This is transmitted. This is fixed, and therefore this will be strong. It will be big. That's why you have this. The other thing that we identify where our mobile device is in this region is that you will have a high throughput. You will have a high data rate on your phone, and which means that it allows you to access the internet and to download movies and then to use it to download fairly quickly. Okay. Now, if we move along and we look at the other side, the lower end of the spectrum, we're here. What happens is the following. So if your mobile is anywhere here, well, you are far away from the eNodeB. You're no longer close to the eNodeB. You're farther away from it. The other thing that we notice when we're here is that your path loss is very large. You have a large path loss. You're far away from the eNodeB. There's a bigger distance, and we saw that the bigger the distance, the bigger the path loss. And if your path loss is small, then you will have a weak signal, right? So this is fixed. This is large, and therefore, when you take a fixed value minus a large, you'll have a smaller receive power, and that's why you will be somewhere here. Your weak signal, by weak signal we mean the received power will be weak, and that's what we see when we are in this region. The other thing that you get when you're here is that you will have a low throughput. You have your data rate is very, very low speed. It's not fast at all. So if you're trying to access the internet, you're trying to check your email on your cell phone, good luck with that, right? It will take forever to load and then to open up and to refresh. And especially if you have attachment in an email, that will take a long time, okay? So that's kind of what I wanted to show you with the mobile signal strength, and hopefully you've captured this by looking at this. It kind of helps you better appreciate and understand how to make sense of a cellular network and how it all makes sense, especially in regards to what we saw before. Right? How do we link it to what we saw before? That's a good way to link it to the previous topics we discussed earlier. So this is good. It makes you happy. You have a good connectivity. This is bad. You have poor connectivity. And if you move even farther away, you'll be in total outage, right? You have no connectivity. What you're hoping for is that as you step out of the region, the coverage for this cell, that there is somehow another cell nearby, and hopefully that cell will serve you, right? And that's the whole process of handoff. How do you move from one cell to another cell while being very smooth? So you want to have a smooth transition from one cell to the other without seeing these interruptions, without totally dropping off, and in other words, to already have some connectivity. And that's a topic that we'll discuss later on. Okay, so I hope that that's understandable. We'll move on to the next topic. At this point, we are ready to see how a cellular network is put together. So how do we assemble a cellular network? Like we said from the previous slide, as soon as you step out of one cell, you will be in outage, and therefore you need to find other means to connect. And other means to connect are hopefully other cells, other neighboring cells that will give you the connectivity that you're looking for. And hopefully all of this is done in a seamless way. So you won't notice it as you move from one cell to the other. It's seamless, it's smooth. If you're talking on the phone, your phone connection will not disconnect. And if you are browsing on the internet, you're still going to be connected. The quality might drop a bit as you regain the signal quality with the neighboring cell, but in general, you shouldn't be in complete outage. So this is what we saw from the previous slide. It's pretty much what we saw there. The only difference is now I just drew it as circles instead of just a straight line where you have all the different powers. It's just a circle. So I wanted to show it to you here just as a reference to always be reminded of what a cell means for us. So it's something like this, and it has different power values. As you go farther away, the power value drops. So at this point, we want to build a network. By network, as soon as you hear the word network, it means that we are talking of more than one cell. So it's a cellular network, and that's kind of what it means. And we want to do that in order to do analysis. Now, when you do analysis as engineers, or when you design a network, when you plan a network, when you design a network, you need to be able to model that. To basically take what happens in real life and express it somehow with graphics or with figures and analytically and basically mathematically. And that's what we're doing right now. So let's look at this. So you have your cell. So this is your cell. Let's say this one here. I'm just redrawing it here with a smaller size, and also I removed the inner lines of the power, but that's understandable, right? You have a cell, and around you have neighboring cells. You have other cells. So this is one eNodeB. This is another eNodeB. This is a third eNodeB. This is a fourth eNodeB, a fifth, a 6, and a 7 eNodeB. And let's say you have others as well, an 8, a 9, a 10. You have all these eNodeBs everywhere. Essentially, in a city, everywhere you go, you should have coverage. You should see these maps, right? They exist, these maps. Perhaps I should include it in future slides. There's a map where you can see the different connectivity that exists, the coverage that exists in, let's say, in this country, in Canada. Of course, you will only have the coverage in the areas where most people live. If you have areas where you have less people living, well, you won't put too many cell towers. You'll just put with few of them because they're expensive to maintain and they're expensive to install. So you only put them in areas where you have customers to use them. So certainly in downtown Toronto, in the different regions in the GTA, in the Greater Toronto region, you'll find many of these cell towers because GTA is a very, very dense region. It is the densest region in Canada. There's a lot of people and they all need to be connected, and therefore you'll find a lot of base stations. So it's very rare to be in an area where there is no base station, right? So what you notice here, we place these base stations, and that's fine, right? So as soon as you're stepping out here, perhaps you're in this region, your quality diminishes, but then you could right away start getting the signal from this guy here. Right, so you could right away get a signal from here. Whereas if, let's say, if you're in this region, you have the option to either continue your signal here, get a signal from this guy, or a signal from this base station. So that's essentially kind of the concept of handoff. How do you move along from one cell tower to another? So let's say you're in a car, you're still connected with this base station, and as you move along, suddenly you right away become attached to this base station. That's the concept of handoff. But right now, let's see the modeling component. This is a nice model. It is somewhat realistic. This is what kind of happened in real life. There is some overlap. But if you notice these areas, right? These areas of overlap, I kind of put them in dark here so you can see them in a better way. These areas where they overlap, they actually cause some problems when we do analysis. So let me read you what I wrote here. Although plausible, this is kind of what happens in real life. Modeling cells with overlapping cells significantly complicates the analysis of mobile networks. It makes the analysis a bit harder to do. So this is something to be mindful of. Okay, I'll just show you another type of changes that we could do to the cell where we won't have overlap. So in this case, we have overlaps of cells. It is somewhat realistic, but the analysis of the network, the design of the network becomes a bit complicated. So let's move on to the next slide. So in this slide, what I wanted to show you is, again, the what we have in terms of neighboring cells that are the other cells that you have neighboring to your own cell, and how they are represented. In the previous cells, we saw that there's a lot of overlap between the cells. Although we said it's realistic, it's hard to model. Now in this case, what we wanted to do is we wanted to avoid these overlaps. So let's say you have the second cell. As you notice, there is no overlap. It's here. There's another one, a third cell here, a fourth here, a fifth, a sixth, and a seventh cell. Right? So one way to do this is to push the cells away when you design your network or when you plan where to put these base stations. Push them farther away, and you'll have that. But if you notice here, you will have this area that I highlighted here, and this area essentially shows the outage areas. And of course, you don't want that. That kind of defeats the whole purpose of being connected. So you do not want these outage areas. So we got rid of the overlaps, but then now our solution is not a good solution. We ended up with coverage holes, and that's also not good. So this model is also not good. It defeats the whole point of being connected, right? So what if you're here, you're walking or you're driving, you're still connected to this base station. As soon as you step out of the coverage, well, you're in a black hole, right? So you have no connectivity. Nobody is giving you any connectivity. This guy is not connected to you. This one is not connected, and certainly this one he just left. So you're lost. You'll be in deep fade or deep outage until you, not deep fade, but perhaps deep outage is the proper word, until you step somewhere, either here or here. And that's not good. We don't want that. We want to be seamlessly connected. So having coverage holes is not a good solution as well. So let's see then, in that case, what do we typically do when we model a cellular network? Well, what's the solution in this case? So we'll see that on the next slide. So at this point, what we saw is two different type of cellular network modeling. Either one type with overlaps where the cells overlap, and the other type where there are coverage gaps. At this point, what we will see is one approach to model your cellular network using tessellating patterns. So we'll show it to you here. So if you see here, this is one example of modeling a cellular network using tessellating patterns. And in this case, the tessellating pattern is an equilateral triangle. Okay, so you have a triangle here, and then within each of these shapes, you have your eNodeB. So that's one possibility. Another possibility to do this is to build your cellular network using square cells. So you have a cell, it's based on cells that have a square shape, and that's another possibility. It is tessellating, and it doesn't have the disadvantages shown earlier. And a third possibility is to use hexagons. So hex for six sides. All the sides have the same size, and they are in this shape. And then you have your eNodeB inside the hexagon. So this is the shape of your cell. It's kind of like a honeycomb shape that you have here. Okay. So if you look at all these three different possibilities, so for instance, with the triangle cells, there are no overlaps, no coverage holes. With square cells, there are no overlaps, there are no coverage holes. With hexagonal cells, there are no overlaps, there are no coverage holes. Right? So these are the advantages. However, one should be reminded that this does not exist in real life. There is no cell that exists in real life that will have a square shape. There is no cell that exists in real life that will have a triangular shape. There is no cell that exists in real life that will have a hexagonal shape. Don't forget, when we identified the coverage of a cell, the gray area here of each cell, it represents the coverage of a cell. We said the coverage will in general be circular, assuming that the eNodeB is an omnidirectional antenna. It radiates in all directions. And that the shape of the cell is also dictated by the different obstacles and objects that you have in the channel, that you have on the ground. Buildings, trees, bushes, other type of obstacles, people walking, cars, all this will dictate the way the coverage of a cell will be. But on average, we said a circular cell makes sense. So if you look at this, none of these are circular, but they are models of what a circular cell can be. So in this table, and I took this table from my PhD thesis, what I did is I compared the different shapes, right? So if you consider a triangular cell, how does it compare to a circular cell? And if you take a square cell, how does it compare to a circular cell? And if you take a hexagonal cell, how does it compare to a circular cell? Don't forget, what we want is something that looks like a circular cell. So if you look at all three, just visually, you don't even need to do math and analysis, you could right away notice that the triangular option is fine, but it's not quite a circular cell. It doesn't look quite like it. In fact, the grayed out area, it represents 59% of the entire area of the cell. So the grayed out area is, you're missing a roughly 60% of your circular cell when you use a triangle. When you use a square cell, you're improving. It certainly improves upon the triangular cell, but still you are missing roughly 36% of your circular cell. Right, so if you use a square, if you look at if you use a hexagon, well, now just visually it looks more like a circular cell. It is not a circular cell, but it looks closer to a circular cell. And the grayed out area is only 17%. So you're only missing 17% of the circle, and so if you simply compare them, well, certainly this one is the winner, right? It is closer to a circle, so it's closer to real life, and in addition to that, it has no overlaps and no coverage holes. So this should lead us to believe that when we do analysis and when we do network design, it is not a bad idea to consider a hexagonal cell. Okay, so you could do that here because of the three key advantages. Number one, no overlaps, no coverage halls, and we saw that both of them are resulted when you use a circular cell. And also it resembles a circular cell, right? So this is the best choice, and therefore hexagon is the winner among these three options. Now, again, I have to re-emphasize that in real life, there is no cell that looks like a hexagon. This is just a model that we use for network analysis and design. Now, this is not only the only model that exists, although this is very traditional. People use this regularly. Also, people in industry use this regularly, the hexagonal cell. But there are other models that came about in the previous years, as of recently. So for instance, I'll show you one approach to model a cellular network using a Voronoi diagram. So if you look in this case, you have what is referred to as a Voronoi diagram. And essentially what it is you have a bunch of points that are generated randomly. And these points, each of them, they represent an eNodeB, a base station. Okay, and as you generate them, then the other thing that you need to do is to figure out how what is the region of each cell. What is the region of each cell? And if you notice, the region of the cells is very random. You have some cells that are large, some cells that are big, and so on and so forth. And this could, in fact, resemble what happens in real life, right? You have some cells that are big, some cells that are small. But this is very random. So you are generating this randomly, and this is how it is obtained. So you get these points, and then based on the points that you obtain, then what you do is you simply find a cell. So what you do is, for instance, I don't know, let's look at this cell here. You have your eNodeB. You look at your neighboring cells, right? The neighboring points. So this is a neighboring eNodeB. You draw a line among each other, you find the middle point, and then you draw a line all the way. And then you look at the other neighboring points. This is the other neighboring eNodeB. You draw a line between this and this, you find the middle point, and then you draw the perpendicular line. And then you do the same thing here, you draw a perpendicular line. And then you do the same thing here, and then you draw a perpendicular line. The points where they intersect, or in computer science, this is referred to as the vertex. This is where you will have the vertices, or the vertices of your cell. Right? So you have the vertices of the cell, and then you could draw the edges of your cell. In every cell, which you see here, the cell shape, this is referred to in computer science as the face of your cell. So that kind of the way by which these cells are obtained. If you notice, not all cells have the same number of sides. So in this case, you have one side, 2, 3, 4, 5. It is because you have 5 neighboring eNodeBs. Whereas perhaps this one here, you have 1, 2, 3, 4, 5, 6, 7 sides, right? 1, 2, 3. This is a small 4, a small side here, 5, 6, 7 sides, 7 sides, and that's how you generate this cell. So not all the sides, it's not like this one. This is, you clearly have only 6 sides, whereas here it varies. The number varies depending on how many neighbors you have. So this is something that I wanted to introduce you to. For us, what we will do is we will continue with hexagon because it also simplifies some of the analysis that we want to do with the channel and with the frequency read. So we'll use this for the time being. I'll explain it. It is still considered, it is still used, and therefore we will continue with this. But I just wanted to bring your attention to different methods that exist. So on the next slide, what I'll show is I'm going to point you to some references that I used throughout the slide. So all the pictures, all the images, all the explanations that I took here, they came from these sources. These sources are some of my previous work in this area, in the area of cellular network modeling in design. Okay, on to the next slide. So in this slide, you will find some of the references that I used throughout this lecture. So the pictures, some of the explanation are here. Now, have you noticed that these are some of my own work in the area of cellular network modeling and design? As you know, that the topic of mobile communication in the basic fundamentals did not change along the years. So the foundation of cellular communication stayed the same. The only variations that happened as we moved along right now into 5G is that the terminologies change and some of the definitions around that change. The use cases change. The meaning of densification in 5G change. The meaning of throughput in 5G change. The meaning of latency, the power, reliability. All these different concepts change, but the foundation, the basic fundamentals of cellular communication, especially at the system level, remain the same. So if your interest is to learn the basic foundations and fundamentals, you could certainly go through some of these sources. I put all the links, so they're going to be there, and I'll try to also remember to put it down below the video in the description below. That's it for now. What we will do next time is we will continue with the with this topic, and at that point we will move into the concept of frequency reuse. We will also discuss the ways that clusters are formed. So you have a bunch of cells that could be assembled together into one family, into one cluster. So we'll talk about how a cluster is formed. What's the rule? What are the rules around forming a cluster? And then once we see that, we'll talk about cellular sectoring, the advantages of cellular sectoring. And that should be covered in that lecture, the next lecture. We will also discuss some of the different varieties of interference that you could face in cellular communication, particularly after applying frequency reuse, right? So if you apply frequency reuse, what impact does it have on interference as opposed to not applying frequency reuse, right? So that kind of gives you a sense of the advantage of frequency reuse and the power of it. That's about that. So I'm not sure if we will have enough time to cover satellite communication. I did want to discuss satellite communication. I think it's an important topic, particularly as we move into the integration of 5G and satellites. But we did lose that week due to the COVID situation, and we have more material to cover on mobile communication. So perhaps we will not discuss satellite communication because of the lack of time, but for your own benefit, for the sake of obtaining perhaps a job in this area, I think your future will likely be related to 5G, because 5G will be enormous in our society, certainly more than satellite. Satellite is coming; it will have a revival soon, but we're not there yet. So 5G IoT will have a more important role. So I think knowing these concepts in a serious way will be beneficial for you, as opposed to kind of diverging right away and then pivoting to satellite. So let's focus on that. Let's finish the concept of mobile communication in a solid way, and I hope you will find that useful. Thank you for your attention, and good luck with your studies.